Hello guys!
Hi, it's your friendly teachers here to
Alright.
teach you.
We're here to teach you Chapter 5, 1 Radicals and Rational Exponents.
Okay, you've seen graphs like this before, but now we want to talk visually just about what we remember with roots. We have two types of polynomials, one with an odd exponent, leading coefficient, power degree, and one with even degrees. If you have an odd degree, then these are solutions that we're going to look at to the equation, the polynomial equation, and the equation y equals c, some constant number. So if you have an odd degree, there's only going to be one solution where that function crosses the horizontal line. But if you have evens, you have three possibilities. You could have one positive and one negative. You could have where x equals 0, that's where we have it right there at the origin. Thank you, I can't think of the word. And where there is no solution at all. Okay? If there's no solution, that our line is down below the x-axis. Okay. So if c is a real number and n is a positive integer, then we can talk about the nth root of c. And it's denoted by one of the followings, the nth root of c, or c to the 1 over n. And you actually already know this, but we're going to take this little concept to a higher level, because in this chapter we actually do some things with exponents, and we look at exponents in a different way. So we need help with that.
So the solutions are the solution of x to the nth power equals c when n is odd, or the non-negative solution of x to the n equals c when n is even.
That's when we have
we're talking about the nth root of c.
Yes. Okay, some basic reviews. You remember how to do this. Notice, unlike the last section, we didn't have negatives under the radical, so we don't have to deal with that first. But we could certainly deal with this as the square root of 48. But there's a better way to do this. And what about look at 6 times 8, and do you see that 6 could be written as 3 times 2, and 8 could be written as 2 to the third? So look at all the 2's we have under there. We have 4 2's under there. So we're looking at 3 times 2 to the 4th. And the 2 to the 4th inside becomes 2 squared outside. This 3 stays underneath, and we would write this as 4 times the square root of 3. Now some of you may say, oh, it's so much easier to do it another way. I know, but we're trying to get you to think a little differently. Okay, let's go to B. Again, we're going to look for perfect squares that are factors, and you want to choose the largest perfect square that you have.
This is 9 and 5. 9 is a perfect square. The square root of 9 is 3, so that would come out, and then we would have 5 on the inside. And then
notice, don't forget, see that big negative sign right there. We are subtracting these two, not multiplying them. Okay, go ahead.
All right, then we have 125, which is 25 times 5. And 25, the square root of 25 is 5, so 5 comes out, square root of 5 is left.
And these are similar terms. Guys, think of this as 3x minus 5x. If that said 3x minus 5x, you know that would be negative 2x. So think of that square root of 5 as like an x, okay? That's what gives you the similar terms. All right, let's go to number C. All right, we want to first of all write this problem. Notice we're looking for the cubed roots. So let's try to write things as cubes. So 1,000 is 10 to the third. X to the third is good, but let's look at y to the 7th. Y to the 7th, the biggest number smaller than 7 that's divisible by 3, because we're doing cube root, is 6. So why not write y to the 7th as y to the 6th times y? Now in our very next step, we can simplify this completely. The cube root of 10 cubed is?
10. And the cube root of x cubed is x. And the cube root of y to the 6th, I have 2 sets of 3 groups of y.
Or you could just do 6 divided by 3
6
is 2.
divided by 3 is 2.
Yeah, y squared. And then there's something that stays on the inside, and let's remember it is a cubed root, so don't forget to write your little index there. And that's our answer. Okay, Ms. Miller, what do you notice in the next problem? The first thing that jumps out at you is?
The fact that this is a difference of 2 squares pattern. We've got 6 plus the square root of a and 6 minus the square root of a, and it's telling us a is positive, so we don't have to deal with imaginary numbers.
Hey, wait, what's the special name for that 6 plus a and 6 minus a? What are those called?
These are called conjugates.
Oh, see, now we have a new math term that we can employ. Okay, so if we just use our difference of 2 squares patterns, we can see very quickly that's going to become 6 squared minus parentheses square root of a squared. and you should know, be able to go straight to the answer, 36 minus a. There you go. And now we want you to try some problems on your own.
So try 16, 30, 34, and 36 in your textbook, and join us when you are complete. Okay.
Calculator.
Now we're going to start with the calculator problems. We're going to use a calculator to approximate each expression to the nearest 10 thousandths. Now remember, 10 thousandths is 4 places past the decimal, not 3 places past the decimal. So we're asking you to give us 4 decimal places. 35 to the 1/8 power. I'm going to go over to my calculator, and I'm going to write 35 raised to the 1/8 power. All right? And I'm going to press Control Enter to give me an approximation. That gives me 1.559, and I'm going to round that to 6.
And if you truncated it, you could leave it at the 5. So 1.5595 or 96.
This is truncated. This is rounded. Okay, then we have this guy over here. You should be able to do this really easy now. This is pretty basic stuff. 285 raised to the 1/12 power. You can put it in parentheses, but it's not necessary in the TI Inspire cast because it automatically puts everything in there until you arrow out of the exponent. Press Enter. Notice it doesn't give it to me. I have to press Control Enter to get the decimal equivalent. So 1.6017 or 1. So this is 1.0616.
601. 1.6017. Oopsie, just erase. 1.6017.
Or 1.6016, and that's truncated.
Okay. Okay, this is the only thing that you have to use the calculator on. The rest of this is all done non-calculators. All right?
All right, so let C be positive real number and let T over C be a rational number. T over K. Be a rational number. Fractions, remember, rationals are fractions, or can be written as fractions, with positive denominator. C over T.
C to the. It's early. C to the T over K
is defined to be the number. Okay. What I always tell my students is that if you've got the denominator in an exponent, it's the root because it's in the bottom, like a tree. The root is in the bottom. Okay. So this is the root, and this is the power. The top is the power.
The leaves.
Okay. Strength. All right. So if I have C to the T over K, it's defined to be, if K is the root, I could write it as, now I could pull this apart with our exponent rules.
You just draw to that too. So.
Yeah. C to the T raised to the 1 over K. That's an exponent property.
And if you look down the line of this equation thing, this right here is the same as that. These are actually all the same, but this shows C raised to some power and then taking the 1 over kth root, the kth root of it.
So K is the root, T is the power. Take the power first. That's what the parentheses, remember order of operations, powers or parentheses are first. So inside the parentheses, then outside the parentheses.
And the reason we're talking about this is because sometimes you'll want to you'll see something like this in the radical form, and you really want to change it to the exponential form because it's going to be easier to work.
I thought I changed the color. The other option here is if you take the root first and then raise it to the power. And so basically written in radical form, it would be the root first and then the power T.
It is very important that you are comfortable with all representations that we have listed above in that equation for C to the T over K. All right, be comfortable with all of those. Don't be afraid of fractions. Fractions are our friends. Froth, F-R-O-F. Fractions are our friends. Okay, now you've seen this before.
You should know all of these from memory.
And so we're not going to discuss them. Let's go on to the next thing. And we're going to use them. So when we look at this, some of you in looking at this would just become overwhelmed. And what we want to do is suggest that you work this in 3 separate parts. So we're going to come way over here, and the first thing we're going to deal with is 16 to the 5/4. Now 16 to the 5/4, look at that 4 down there, that is our root, and so we want to wonder if there is a way to write 16 to the power of 4. And it is, it's 2 to the 4th, and raising that to the 5/4, what is it we do with exponents?
Well, when they're raised to another power, we multiply them.
And so the 4's will cancel, and you end up with 2 to the 5th. Now we'll deal with that a little more fully in a little bit. Now, change colors maybe, and let's look at x to the 2/5. Okay? X to the 2/5 is going to be raised to the 5/4. Once again, you multiply the exponents. Do you see that 5 in the denominator and the 5 in the numerator? They're going to cancel out. Okay? And you get x to the 2/4, which you certainly can see is x to the 1/2. Okay? And now we're going to look at y to the negative 1/4, and y to the negative 4, raising that to the 5/4.
Well, 4 times 5/4 is, those cancel out, the 4's cancel out because you have negative 4 over 1 times 5 over 4. All right, so those factor cancel out. So we've got y to the negative 5.
Okay, and we know that y to the negative 5 is 1 over y to the 5th. Notice it says up there write only using only positive exponents. Now we're going to combine all the three answers we got. So if we come back here, 2 to the 5th we now know is 32. We want to go straight to what we know about it. It's 32. X to the 1/2, that stays on top. And then on bottom is this y to the 5th. And there is your answer. And this is what you want to do. So if you're trying to do this any other way, I promise you it is going to be much more tedious and difficult. So when you do the ET problems associated with this set of examples, please try to use the methods we're showing because this is going to be an important skill for things coming up.
Notice that in this problem in particular, there was no plus or minus sign in between the terms. This is a monomial, not a binomial. And when we raise a monomial to a power, you raise each term to the power. If you raise a binomial to a power, you have to factor, FOIL, whatever special pattern.
Yeah.
All right, so be careful when you're doing
pay
that.
attention. The signage is very important. Now, if we look at this one, notice that this, see that big subtraction sign in the middle there? That means we're going to distribute because that's like an A plus a B thing going on.
This is not a power. This is a number being a
Coefficient.
coefficient being multiplied by each value inside. Okay.
So what we're going to do is we're going to go ahead and write this y to the 1/3 plus y to the 1/3 times 1/6 minus y to the 1/3 times y to the 5/3. Now, what do we do with those? You know that when we have these, we add the exponents. So let's next step go straight to y to the 1/3 plus 1/6 minus y to the 1/3 plus 5/3. Now, the second one's really easy because we already have the common denominator. The first one is simple to find the common denominator, but a really easy thing to do on that first one is there's this little SAT trick when you have two fractions you're adding together. It's just, with different denominators, 1/3 plus 1/6. You take the product of the 1 and the 6 times the product plus the product of the 1 and the 3 over the product of the denominators.
So 3 times 1 is 3, 6 times 1 is 6, 6 plus 3 is 9, over 18, which is 1/2.
And you do it in this order, though. You always do the 1 times the 6 first, plus the 3 times the 1, because if that is a subtraction sign, the order that you do that matters. So now you can see that we're going to have y to the 1/2 here.
And this is y to the 2, so y to the 1/2 minus y squared.
And we're done.
And we're
That's all
done.
we can do.
Okay, so here's another one.
Okay, now when you see this one, notice the second factor there has an exponent that is negative. Some of you would immediately want to deal with that, but in this problem it is so much easier to just raise each factor inside of there to the -2. So what we're going to do is rewrite the entire problem as x to the 7/3, y to the 3rd, and then x to the -2, and y to the 5/6. Oh, okay. To the
Times -2.
Okay.
That works.
All right.
And then 5/6 times -2, the 2 and the 6 would simplify this out to a 3, so this is -5/3.
Okay, so we have x to the 7/3, and let's put
The
other x.
So we have x to the -2.
And then y to the 3rd, and
And-
then y to the negative 5/3. Now, again, you could be flipping out over this, but look, you've got x to the 7/3 and to the negative 2. Remember, what we do is we add exponents, so let's just make that equals, okay, x to the 7/3 minus 2, which is plus a negative 2, and times y to the 3 minus 5/3. And now you have to go back to middle school to do all that, and we're not going to do that for you, so you get x to the 1/3, y to the 4/3. Okay, you really should be able to subtract those. All right, so we're going to go on to this next one because it's actually much more interesting.
Okay, so let k be a positive rational number. Write the expression without radicals. Oh goodness. Using only positive exponents. Okay.
So this is like that at the beginning where we said we really want you to get comfortable using fractional exponents. Okay.
So remember, the bottom is the root, the top is the power. So the first one can be rewritten as a to the 4k over 12, which is
okay.
the same thing as a to the, 4/12 is simplified to 1/3, so k over 3. All right?
Okay, let's do the next one a little more methodically. That a to the negative k to the 1/3, and that is the square root, so that's to the 1/2. That looks horrible looking at all of that, but look at what you've got there. See the 1/3 and the 1/2? That's 1/6. So you now are looking at a to the negative k to the 1/6, which gives you a to the negative k over 6. Now, it says to use only positive exponents, but that doesn't mean in the working of the problem you have to use only positive exponents. It just means by the time we get to the end. So our next step is to take the two things we've actually found, which is a to the k over 3 times a to the negative k over 6.
Okay. So now, since they're being multiplied, we can just add the exponents, which is a to the k over 3 minus k over 6. And that would give us, from elementary math, a to the k over 6.
For those of the unenlightened, k over 3 is the same thing as 2k over 6, so 2k over 6 minus 1k over 6. Got it? Got it. Good. Okay.
So go ahead and try these problems in your textbook.
Yep.
Okay. Rationalizing a denominator. We've done this before.
Algebra 1, geometry,
Lots in
algebra
geometry.
2, and OG just a couple of weeks ago. So this one's an easy one. So you can see that what we need is that square root of 6 needs to go away from the denominator. So we're going to multiply the whole thing by square root of 6 over square root of 6. Boom, there's your answer. That's nice. What about the next one? Well, by the conjugate of the denominator. And you have to multiply the top and the bottom by it. Now remember, what we taught you to do is to look at that, recognize that what you have there is a difference of two squares in the bottom. So in the bottom it should be really easy to just go straight to 16 minus 5. Okay, the top you're going to have to...
Okay, so we're going to try to distribute the 3 to the 4 and the negative 5/3. All right, so we've got 12 and then minus 3 to the square root of 5. 3 times the square root of 5. So now we can go ahead and
simplify the denominator. Now, what I would typically do, that's the answer. You can't do any more with that. But I probably would hold off on distributing on the top until you've simplified the bottom, because let's pretend by some magical thing that, I don't know, you got 3 on the bottom. Wouldn't it be nice to cancel? So you might want to hold off the actual distribution step on the top until you see what the bottom becomes. But, you know, in this one it worked out nicely and we're done. And now we just have one more example. Now, look at this one we just did. The one we just did, we were rationalizing the denominator, because you've always had teachers say you can't have radicals in the denominator. Well, guess what? Sometimes when you get to more advanced topics, you actually have to get rid of the radical that's in the numerator. So we're going to do the same procedure we just did, but this time we're going to multiply by the conjugate of the numerator, and we're going to end up with a radical in the denominator. So what happens when you do this is you have heavy-duty algebra, but follow the technique you know and you should still be able to do it. So we're going to multiply by the square root of 2t plus h plus the square root of 2t. Now, on top...
It's the difference of two squares.
Yeah, and you want to probably be a little more deliberate in your work here so you don't get confused. So we're going to write the first one as the square root of 2t plus h, the quantity squared, minus parentheses the square root of 2t, the quantity squared. That's on top. On bottom, you definitely want to leave it factored. H times parentheses square root of 2t plus h plus square root of 2t. And that's it. Now, on top, we can simplify that because you know that that square root of that, the square of that square root thing gives the radicand. So 2t plus h minus, and the same thing over here. Now, I would like to caution you, if you have more than just one term, one term here, you need parentheses because you might have to distribute a negative. And again, always leave the denominator factored in a problem like this because the ultimate goal you'll see is what's going to happen. What happens next?
All right, well now we've got 2t minus 2t, and those cancel out, so now we just have h in the numerator. And we have h in the denominator. Ooh, that's nice. Square root of 2t plus h, that's in a square root, plus the square root of 2t. And now the h's factor out, and we get 1 over the square root of 2t plus h plus the square root of 2t.
Right. And that's it. Now, I know that looks ugly, but down the road, we're actually, those of you that continue in math for whatever purpose you have, down the road, you're going to be looking at what happens when that letter h in this problem becomes so small that it gets close to 0. Well, you can see from this step right here, if h is actually 0, you're going to get 0 over 0, and that is a big problem. We call that an oh no. And so you actually have to do a little more algebra, and now if you were to go to this step here, you can see that if h is 0, it's not going to give you a 0 over 0, it's going to give you 1 over a bunch of stuff. And that's the bottom line, is down the road, you're going to need to be able to do some simplifying, so there's heavy-duty algebra. So that's why you want to know this.
All right, go ahead and try 74, 76, and 85 in your textbook.
And thanks for watching.
So, do we ask them to...
I forgot. Yes.
All right,
Pause
so
it, just pause it.
To confirm that you have indeed watched this video, email your teacher by 8 a.m. By the day you have class with the following information: 1 new thing you learned, 2 good questions, an old skill that's important to recall for this material, and your subject line for your email should be 5.1 video. We're getting, at least I'm getting, a lot of different names for the video. It's getting slightly confusing in my email box. So if you want to get credit for the email, please put 5.1 video as your subject line. And don't forget to bring your entrance ticket, problems, and completed notes when you come to class.
Thank you.